I am Dr. P.S.V.Shanmukhi, Associate Professor, Department of Physics, Aditya University. Now I am going to explain about the Einstein equations in semiconductors. So at the end of this lecture, student will able to understand the drift and diffusion currents. You can also derive the Einstein equations in semiconductors. Now coming to the drift currents, what do we mean by a drift current? Generally, this is a semiconductor slab or a conductor. Whenever it is subjected to some electric field is applied E bar. So in presence of electric field, suppose it is a semiconductor slab, there are some electrons and there are some holes also at any temperature. Generally, the holes will travel towards the positive terminal and the holes will travel towards the negative terminal, electrons will travel towards the positive terminal of the battery. So anyhow, in presence of electric field, the charge carriers will have some velocity that is known as drift velocity, and corresponding current is called drift current, corresponding current density is called drift current density. That means drift currents are nothing but the current density are in presence of applied electric field, the charge carriers will have some mobility, they will produce some current. Those currents are called drift currents. Corresponding current densities are called drift current densities. Generally, we have one expression J is equal to NEVD, V suffix D. Vd, the drift velocity. Another expression we know that is J is equal to sigma into E. The current density J is equal to sigma, that is sigma the conductivity, E is the electric field, applied electric field. So generally what we write is Vd is equal to mu into E, where mu is the mobility of the charge carriers. So anyhow, J is equal to, you can write Ne into Vd or Ne into mu E. Why? Because Vd is equal to mu into E we can write. So J is equal to Ne into mu E. So there are two types of charge carriers in a semiconductor, electrons as well as holes in an intrinsic semiconductor. So what is the drift current density due to electrons? What is the drift current density due to holes? That what we have to see. So in presence of means in case of electrons, we can write the drift current density Jn drift, it is equal to Ne into mu E into E, where N is the electron density, E is the charge of the electron, mu E is the mobility, and E is the electric field, applied electric field. In the same way, the corresponding current density due to holes we can write Jp drift, it is equal to Pe mu H into E, where P is the holes density, E is the charge of the electron, mu P mobility of holes, E is the applied electric field. Suppose in a semiconductor, the current is due to both electrons and holes, say in an intrinsic semiconductor, and the current density, the total current density can be written as J drift is equal to Jn drift plus Jp drift, Ne mu E into E plus Pe mu H into E, or else we can write E into E is taken out, N into mu E, P into mu H. Generally in case of intrinsic semiconductor, at any temperature other than 0 degree Kelvin, number of electrons is equal to number of holes, N is equal to P is equal to Ni, that is called intrinsic carrier density. That's why we can write this J drift is equal to Nie, E into E, that is mu E plus mu H. This is the expression for the current density, total current density, drift current density due to electrons and holes. So simply drift means in presence of applied electric field, the current density or the current is called drift current, current density is called drift current density Jd. Now coming to diffusion. Suppose imagine there is some region in a semiconductor, more concentration of electrons here, less concentration of electrons here. Generally the carriers will diffuse, they will move from higher density to lower density. That kind of motion is called diffusion. So carriers are moving from higher density to lower density. That kind of motion is called diffusion. And diffusion, they will produce some current automatically, that is known as diffusion current density. Generally, the diffusion current density, it is proportional to the concentration gradient. What is that? Along x direction you are taking dn by dx you can take. Along y direction dn by dy. Anyhow, one dimensional system let us take. It is proportional to dn by dx, or it is equal to some proportionality constant, that is dn into dn by dx, where E is the charge of the electrons, dn is called diffusion coefficient of electrons. So therefore, what is J and drift current density? E into dn by dx, where dn by dx is the concentration gradient variation, dn diffusion coefficient of electrons, E is the charge of the electrons. Anyhow, next coming the same way, in case of holes, how do you write the diffusion current density? That is actually written as minus E into dp by dx. Actually, capital dp diffusion coefficient due to holes, P stands for holes, dp by dx, that is the holes gradient. From higher density to lower density they are moving, minus E. Actually, in case of electron there is no negative sign, in case of hole there is negative sign. Why? Because generally the diffusion is from higher density to lower density, from higher to lower. So the equation you have to write, J is proportional to minus dn by dx we have to write. So in case of electrons charge is minus E, that's why finally we are getting plus E. In case of hole charge is plus E, that's why we are getting finally that Jp diffusion is equal to minus E dp dou p by dou x. That's why negative sign difference is there like that. So in the same way, if both the electrons and holes are there in a semiconductor, both are causing the diffusion current densities, then how do we write the diffusion current density? J diffusion is equal to E into dn by dx minus E into dp by dx. We can write like this is the diffusion current density. Now, suppose in a semiconductor slab, there is a concentration gradient, higher density, lower density, concentration variation is there. At the same time, the material is subjected to this kind of one applied electric field is acting. So what happens? The concentration variation is producing the diffusion current, applied electric field is producing the drift current. So if both are there, what is the total current density? Drift current density plus diffusion current density we can write. Therefore, this is the diffusion current density equation already we have determined, this is the drift current density already we have determined. The total current density J total is equal to E is taken out, for electrons and holes E is the charge common. Therefore, we get the final equation like this. So, these are known as drift currents and diffusion currents. Coming to Einstein equations. So, this is giving the relationship among drift and diffusion currents. Anyhow, suppose if there is an equilibrium state, the electric field is acting in this direction and the diffusion is there in the opposite direction, say automatically at equilibrium. Suppose the drift current and diffusion current density is due to excess electrons, it is equal to this one. That means dn into E into mu E into E, that is due to drift, and E into dn by dx, that is due to diffusion. Actually this dn, it is the excess, actually n E mu E into E, we write like that. Instead of n, the excess carriers, that is dn. These excess carriers are causing the diffusion also. At equilibrium, these two current densities must be equal. So now, equating these two, we get dn into E is equal to E dn by mu E dn by dx we get. Actually, according to this Einstein, these excess electrons are just given by the force. The force equation dn into E remaining RHS E dn by mu into dn by dx we write. Actually, according to the thermal according to kinetic theory of gases, so the force due to thermal energy, it is written as F into kBT, kB means Boltzmann's constant, into T absolute temperature, dn by dx, that is the concentration gradient. So in that way, F is equal to kBT dn by dx we write. Then these two equations, equate equations 1 and 2, what do we get here? E into equation from equation 1, E into dn by mu E dn by dx is equal to equation 2 kt into dn by dx we write. Automatically simplifying this one, the dn by dx is cancelled on both sides. You will get kt into kbt is equal to E dn by mu, we get like this. Or what is dn expression? Dn is equal to kt mu E by E, we get like that. This is the diffusion quotient due to electrons, or else we can write dn by mu E is equal to kbt by E. This is one Einstein relation. Similarly, if you take the p-type semiconductor, actually n-type semiconductor electrons concentration we have taken. In the same way, we take the p-type semiconductor, what do we get? Instead of dn, we get dp. dp by mu h is equal to kb, as usual Boltzmann's constant, t by E, charge of the carrier. Automatically dp by E we get. So, that is dp by mu h is equal to kt by E we get. From these two equations, what do we write? dn by mu E is equal to dp by mu h. This is known as Einstein equation, and this is giving the relationship between the diffusion quotients due to electrons and holes. The diffusion quotient of electrons dn, diffusion quotient of holes dp, and mu E, mu h are mobilities of electrons and holes. This equation is known as Einstein equation. So, coming to the summary of this one, what we have discussed in this one is, we have discussed the drift currents and diffusion currents. Suppose if there is means applied electric field, the carriers will move from so one place to another place, they will produce some current density or some current, that is called drift current, and the corresponding current density is called drift current density. When there is a concentration gradient, concentration variation, automatically the carriers will move from higher density to lower density, they will produce some currents, that is called diffusion currents. Already we have seen the expressions of those two. And finally, we have derived the Einstein equations in semiconductors. Thank you.